Don't take little incremental steps, but go do something else where it's not being done.
We're living evolution. I mean, this is a living example of how it works.
Innovation is finding new ways to do things and building tomorrow's world. Today, we're talking with two high-technology pioneers. Gordon Bell, National Medal of Technology awardee, invented the first mini-computer, the first commercial time-sharing system, and led the VAX team as head of Digital's R&D. Carver Mead's revolutionary ideas resulted in the classic book on integrated circuit design. He's taught at Caltech for 33 years and is pioneering neural technology there and in Silicon Valley. Research scientist Steve Omohundro moderates the discussion.
Both of you have been involved with several companies, and how has that work compared with more pure research that you've done?
Pure? What's pure?
Yeah, how do you...
That's actually an interesting idea. That's an anachronism, but it was very common in academia 30 years ago that there was such a thing as pure science. I think the idea began to go out of style when solid-state physics developed as a result of the transistor. And it became very clear that the best fundamental research came out of the devices that emerged from the commercial sector. And so that wall started crumbling between what was pure and what was sort of crass commercialism.
Applications drove underlying theory and ideas.
Well, and they gave us the tools. I mean, with semiconductor devices, we could look at parts per billion of stuff, and we could see effects that you could never see with standard chemical analysis and all that. So we just opened up an enormous amount of fundamental physics by these devices which were done for practical purposes. So it's never true that there's this division line somehow, and if you're on one side you're pure and you're all tainted if you're on the other side. It just doesn't work that way. That was an old view. I think that came from the separation of church and state or something, but Middle Age sort of idea.
And that whole idea, unfortunately, I think is carried forward of the idea of these stages that really contaminates a lot of work today still, which is that you go through these stages of basic research, applied research, advanced development, product development, and then into sustaining engineering. And that's not really how, for example, our friends in Japan work. I mean, they get in and start probably from or in many cases start from a product, use that and evolve that product as a way of producing advances, as opposed to saying, gee, if I start in a lab and go work from that point of view, and then ultimately that will come into a product as you go through these stages. And so I think we have to totally refine our views, particularly when you've got these very fast product cycles, and in many cases the companies themselves are leading the work.
You hear a lot of things about products coming from the market demand, and that's not where products come from. Products come from someone seeing what's possible. And very often the whole idea of market research doesn't ever unearth the good ideas, and they're the classic examples of the HP calculators and the IBM study on the 70 whatever and so forth, that we're all so way off on market research. So that products really do come from the coalescence of what's possible with an idea of what the need is out there. And that's really the genesis of it. So, and that's where research, quote, research, that the new ideas of what's possible comes into the thing. But the part that always gets left out of that is that once a stream of product development or device development or whatever starts going on, that feeds back into people's ideas of what to look at. What are the fundamental questions? And you don't find out what fundamental questions are by, you know, contemplating your navel or looking at the stars or whatever. You get them by grappling with trying to do things. And that's why Gordon said, you know, when you're doing something, all of these fundamental ideas come up that you may or may not have time to chase down and figure out, but they come out of, you know, this tussle with reality.
The big disasters really come from these marketing departments getting to a point where they're specifying to an engineer, you will build this. Here are the specifications. And what they do is really go out and read every other product spec and say, we'll want one of those, one of those. And it's got, of course, it's got to be cheaper, it's got to be faster than everybody else. And so it's an amalgamated things. Of course, there's no ideas in it. And when you amalgamate every idea and every other characteristic, functional characteristic in a product, why it's bound to be a disaster. And the biggest, I think the biggest disasters have come out of these sort of product, these market-driven things, as opposed to I'll say a technology meeting a market.
Yeah.
Means you've got to meet the market. You've got to go out and get the market and say, yeah, I think I can make this thing to solve a problem. And so
But that's more of a
different. Yeah.
You know, that's more of a problem-solving mentality. It's the marketing orientation by the person that has the technology at their fingertips.
Who knows what's possible.
Right, and it's that coalescence of there's a problem to be solved, and I think I could see how the technology could do it, and that's the creative part of a product definition thing. But the typical marketing, in quotes, you know, with a capital M and the sign over the door and stuff, that all is about analytic continuation. You look at trends and you say, gee, it's going to keep going like that.
You don't see anything new.
Right. And you don't ever see what we call generative markets, the things that come up because they're enabled by a technology, and those are always the great ones. The analytic continuation things, you know, pretty soon you get overrun by everybody, the horde of lemmings going down the same path.
And large companies building and saying, gee, we've got to be in this market. They start with the marketing department saying, yeah, we'll do that, and now let's get some engineers, throw them together, and cook us up one of those to meet this market demand. And that's when you have, you know, some of the biggest disasters.
Can you give us some examples from your own experience where some new direction was suddenly, you were aware of the technology and you were able to push it, and that has led?
Well, there are historic examples, of course, and they all had to do with everyone going one direction and hammering on things, but it ended up what was being hammered on wasn't the next step. So like in the semiconductor end of it, you know, people were beating on vacuum tubes, and then there was this solid state device. And then we all went off, including myself, and went roaring off on solid state devices. And then Bob Noyce came along and saw how to interconnect them. So the integrated circuit came as another direction. Hadn't to do with the transistors, it had to do with how to interconnect them. And then, you know, just about the time when a bunch of us were going off deciding how to design those things. And then Federico Fagin came along with the microprocessor, which was how to not have to design so many of them. And then just as everybody was going off with, you know, standard parts and you got to program them and stuff, and then the silicon compiler came along, which was how to design them easier. And so it keeps being a way of doing things that's different than the paradigm, the zeitgeist. Absolutely, look at it a different way. And you can see things in a new light and see how there's a way of doing business that just looks different when you've done it. When people talk about Gordon's kind of teraflop computers, they always get asked, what are you going to use this computer for? And they say, well, we're going to do real-time natural speech, and we're going to do vision, and we're going to do all these biological perception problems. Well, it is true that those problems take, you know, these arbitrary amounts of computation to do, but it's also true that that isn't the only paradigm for doing that kind of computation, and that the digital machines that do discrete symbol manipulation are are not exactly matched to this very soft kind of fuzzy computation that goes on in perception systems. And the neural technology that's coming along on silicon also, so it's piggybacking on the same base technology that the digital stuff is driving, are evolving now to where we're starting to be able to do really very competent things for like 10,000 times less energy than you can do them with the same technology used digitally. So that's another sleeper with sort of a right angle turn.
Paradigm
and,
shift.
you bet.
Yeah.
And so just about the time, now don't get me wrong, people will find really good things to do with those teraflop computers, but
Yeah.
it's not going to be speech and
No.
vision. Those are going to be done with these neural chips that work on a different
Yeah,
paradigm.
at most those machines could be useful in doing training for you, but that's about it.
Yeah,
I
we're
mean,
using
you're-
them right
you're
now
already-
to
you're
design
already
the
used-
chips.
Yeah, right, where you need lots of flops.
Oh, and
but-
we can use as much
yeah.
as you can
But
give us there.
in design, but you know, and the scientific community can use as much computing as you can ever throw at it, because in terms of bringing more of the world into it,
Absolutely.
whether it's simulating the, you know,
Oh, don't ever make the mistake of
the,
saying
the
what
super
could,
collider or
you
what.
know, what could people possibly
Yeah.
do with computation. Don't worry.
Yeah,
They'll find a way. It's just fine.
Yeah.
That's not the problem. But it won't be what they foresee. And that's one of the lessons you learn. You know, we always get asked, what are you going to do with all this neural technology? And we always say, well, we could see some things that'll happen, and yes, we'll do real-time speech, connected speech, we'll do, you know, vision of various things. Yeah, but those are long-term things. But Federico tells this wonderful story about the microprocessor, and when the microprocessor came in, we could all see that there would be a personal computer. There was no question. I mean, all of us saw that.
was,
It
yeah,
was trivial.
because we had big personal computers at that point.
Right.
That people were buying $10,000 personal computers,
But what we didn't see
didn't
was
see.
they'd be in the gas pumps, and
Yeah.
in the microwave ovens,
Yeah.
and in the
Every-
electric drills, and
everywhere.
in the wheel balancers,
And in the watches.
and we didn't see that at all.
Right.
You know, it's just a different way in which the applications come up when the technology is there to use them, and you get hundreds of times more things you didn't think of than you get the things that you did think of.
So let's say you're looking for that. How would you stimulate it? How would you cause yourself to be aware of those shifts of perspective?
Well, for me, it always starts with a dissatisfaction down in the gut. It's never articulate. It never has. It's very fuzzy, and it gets this. It starts with a kind of an itch that I can't scratch, and then I notice that whenever anybody brings up the subject, I get very irritable and snap at them. And that's when I know that something's going on. And then gradually it gets to where I get more and more angry with the way people are doing things. And then at some point, I'm able to articulate why or how or something, but it's much later. It's almost fully formed by the time any words come with it. And the rest of it is this antisocial behavior that do you get into those?
I mean, I was trying to reconstruct when those things happen and what we were all trying to do. That there's the mainstream is going a particular way, and you know that's not right. I mean, the one that I recall probably most recently was it's back a decade, and that was this whole idea of we've now, you know, we knew that the microprocessor was on a strong evolutionary path, that they fundamentally cost nothing, and now clearly you can make a microprocessor and then a microcomputer that goes into nothing and costs nothing, and so you got your whole life in your in your pencil or your whole PC there. And so for me, who like to build bigger machines, I say, well, what can you do? You've got to tie those together in some fashion.
When you're in the middle of it, there are always little things. There's no, or very seldom there's a huge thing. It's just you figure out one more little thing.
Small frustration that you want to get over.
Yeah, and then you wake up one morning and you see how to do it, and it's very satisfying until you run into the next one, and then you're frustrated again, and you get used to that. I mean, it's exhilarating because you are making progress, but it's not like there's one moment and there's this giant aha, and now you're good for another 10 years. It isn't like that at all. It's just, you know, it's more like, you know, climbing a very large mountain over boulder-strewn surfaces that would be easy to fall down in. It's a lot more like that than it is like some giant leap that all of a sudden solves all the problem. You read about those things, but it doesn't feel like that when you're there. And I'm sure there are things of that magnitude.
You get local ahas, sort of. I mean, all
and
the
those
time.
are wonderful.
Yeah,
but
right. But
if anybody ever asked you what
Right.
you did, you said, well, mumble, I did this dumb little thing. And it's very exciting to do it because you know it's in series with doing something that's really important. But to try to explain to anybody why it's important is it's part of a long chain of things that all have to work to get there. And it's a long chain, and any one link looks just like a dumb little piece of stuff. And,
Do you wake up one day and realize that suddenly you're looking at this problem differently than everybody else is?
oh, sure. Oh, sure. But I mean, that's nothing new. I mean, we've been crazy for a long time.
yeah, and I think it's after there's enough out there. That is, you've seen enough. You know, you've built enough things, and you've got it out there. Then you can back off and look and say, hey, there is more of a pattern here. There is a general theory here, and you can structure it from that point of view. But it's after you sort of been building all of these things.
Grappling with them.
Then you build a kind of a general theory of the universe based on this.
Or in hindsight.
Based on absolute hindsight.
Yes, all order
Yeah.
in the universe comes in hindsight. It's
Yeah.
you know, evolution is a process that works kind of bottom up, and there, you know, you get these little local things, and you
looking
get
at it.
something, and you're frustrated because there isn't the other thing, and you don't see out of it, and I mean, the evolution in the organic world worked the same way. I mean, it has this wonderful order to it in hindsight, but as it was happening, there are all the dead-end streets and the cul-de-sacs and all of that stuff that wasn't so well ordered as success would dictate looking backwards. So you look for the missing links, and why can't you find the missing links? It's because the whole surface of the earth is strewn with all the things that didn't work out, and that's the way it is with technology, that almost everything you do doesn't work out, and it's just finding the little ones that do, and often you don't know which one it's going to be.
Which line is the mammals?
Right. You just really don't know until you got to have hunches, but you don't really know until later, and then you look back, and if you're honest, you say, yeah, you know, and if you're not honest, you say, oh, I was so smart.
You both managed to sort of be a little ahead of the game in several instances. How do you sort of force yourself to persevere against the mainstream, to notice this frustration and proceed ahead?
You know, I think it's seeing that, really trying to see that there is something, there's a much better way of doing things, and that you want to do it different. And I guess my point is I don't particularly need to do anything that somebody else is already doing. I mean, there's a piece of that of, hey, if they're doing it, I assume they're competent. I'm willing to let them have the damn thing, and I'll go off and do something else. And so I think that the message here to everybody is, hey, if somebody's already doing it, you know, and they've been at it for a while, and don't take little incremental steps and go do that, but go do something else where it's not being done.
I think it's what Gordon said, that you have this image in your head of how it can be, and if you could just get there, it really would be a much better. And you try to explain it to people, and they don't see it because they can't experience it. But you can see it in your head. And so that gets you to persevere until it's far enough along that then you can show it to people. And then once you can show it to people, people say, oh, that's kind of neat, or they say, oh, you're crazy, or whatever they say. But they're,
I see that.
yeah, yeah, well, yeah. There's that awkward period when then it becomes, oh yes, I invented that too. Right? So that's about a year later. But there is this time when people start to see it, and there's a wonderful, wonderful feeling of being able to share that thing that you've had in your head for so long with people, and they like it, and I think all of us like to.
Can you talk about a specific situation where that happened?
Well, I guess we've all had lots of them, but certainly the business of compiling chips was a thing that I found particularly satisfying. Everybody's doing that now, and it's the first times I started talking about that, it was like
crazy.
man on the moon.
Yeah.
It's,
because everybody was used to doing them by hand.
and then we built little compilers, and then Dave Johansen went off and created a really quite substantial compiler, and then Gordon came and got us to teach a course back at DEC and get their guys involved in it, and gradually, just...
And was there resistance at that point?
Oh, by then, yeah, there was still... actually, just this last couple of years, the semi guys have been doing a lot of it.
Well,
it took 20 years. People don't often say, and it's worth saying, is that down through history, if you look at innovation, at least in technology as we know it today, there have been what I call golden periods. Like in the electrical power business, there was a period of about 15 or 20 years where it went from almost nothing to the complete paradigm that we enjoy today in our power system. And it all coalesced in that period, and it was just this golden age, and it all happened. And then it's been the same ever since. And that happens.
There was a tremendous need, and suddenly it could be fulfilled.
Well, it was not really a need. It was a sense of the potential, and a determination, and this sort of sense of the possibilities, and the intrigue of wanting it to happen, and then the people that could be users getting excited. It's very interesting. But if you look down through, the same thing happened with radio. There was a period of about 15, 20 years when all of what we now have in radio, up until the time of spread spectrum stuff, all came into place. All the inventions, everything. And by the way, television happened over a period of about 10 years. And do you know when the NTSC standard that we use today was put in place? 1941, pre-war. And we haven't changed it since then. All of that stuff happened. It was this golden age when that came together. And we've seen that with the semiconductor age, which happened in the 60s, which there was this enormous flowering that resulted in the integrated circuit. It's sort of at the end of it. And then we've had the microprocessor thing that started in 71, 72, and then it gets to be the art form that it's going to be, and then it has to be some other paradigm that takes the next one. But there are these wonderful ages when just flowers, and after every one of those, everybody thinks, well, that's the last one, and now and that particular thing won't change. It'll just evolve ever so slowly, but there will be the next golden age. There will be, and we're in the middle of one right now, and it's absolutely exhilarating.
The clear two big ideas of this century were the transistor evolving into the integrated circuit, and the integrated circuit is the big idea, and that evolution, or that constant exponential evolution, embodied in Moore's law, that says that the density will quadruple every 3 years or double every 18 months. That's been driving us solidly since in the mid-60s when the first ICs came out. And so we've been on this thing, and people argue a little bit of, well, gee, maybe it's going to double every 2 years instead of 18 months or 2.5 or 3 years. You know, I wish it would a little bit, and it would give us a little more time to know what we're doing. But fundamentally, we've been on that constant evolution. That's the thing that I can at least, let me say, put on one of my hats as a historian. I can trace everything pretty much simply into this Moore's law. That is the way all the computers develop, the way all the computers classes form out of that, the microprocessors form there. The fact that more memory, that you double, that for the same amount of money, you quadruple the amount of memory you have on your system every 3 years. And that's been their big drive. Or conversely, the memory you had on your system is a quarter of the price, which means a whole bunch of other people are going to buy computers, or whole new classes of computers are going to form.
Let's talk about Moore's law just a little bit, because
Something everybody should know.
After it's happened long enough, people begin to talk about it in retrospect. Mm-hmm. And in retrospect, you know, it's really a curve that goes through some points. And so it looks like a physical law, and people talk about it that way. But actually, if you're living it, which I did, and still am, in fact,
I think you're still,
then it doesn't feel like a physical law. You see, it's really a thing about human activity. It's about vision. It's about what you are allowed to believe. Because people are really limited by their beliefs. They limit themselves by what they allow themselves to believe is possible. So here's an example where Gordon, when he made this observation early on, he really gave us all permission to believe that would keep going. And then so some of us went off and did some calculations about it and said, yeah, it can keep going. And so that then gave other people permission to believe it could keep going. And as that evolved then, people could start, well, yes, I've believed it for the last 2 or 3 generations. Maybe I can believe it for a couple, even though I can't see how to get there. And Gordon Moore always said, well, yeah, you can see about 1 generation into the future, and then it gets really scary. But if you see it over that whole thing, you say, gee, well, maybe, even though I can't see, and it's scary as hell out there, maybe I can believe 1 step beyond that. So then you put your energy into that belief. And guess what? When you put your energy in, then you can cause it to happen.
It's amazing, yeah.
And then other people can believe, and by now you've got the whole world believing this can happen.
So Moore's law is a non-frozen paradigm. It's one that has built into it growth.
It has a dynamic built into it.
Oh, yeah. I mean,
So
and never an exponential like this. I mean,
Absolutely.
look at that exponential. Nothing in history has ever behaved this way.
Oh, there are rat populations and things, but you know.
Well, but they're. But if we could count them, but I mean, even they run out of food and they're getting constrained. And, but the thing that's happened with it is that it is the thing that does explain all the industrial structure in there and all of that how machines have formed and what can be built. I mean, it's a law we depend on. I mean, it's not quite as, you know.
Yeah, wonderful thing about it is that it's not a static law, that it forces everyone to live in a dynamic, evolving world. So, you know, instead of just thinking about Darwin said that evolution happened, we're living evolution. I mean, this is a living example of how it works. It's turbulent, it's not pleasant, there's a lot, but it is exhilarating, it is wonderful, and it's the only way to get there. And we're living that every day. And we have this so-called law, which is really a thing about the possibility of the future. It's absolutely wonderful because there's never been such a thing. People never allowed themselves to have a constantly expanding view of the future before, ever in history of the human race.